Hi, we will learn chapter 18, and we will learn 4 basic thermodynamic processes applied to ideal gas: constant temperature, constant volume, constant pressure, and net heat transfer is zero, adiabatic process. Also, we will learn specific heats of gases. And first law of thermodynamics is nothing but energy conservation. We can imagine there are two ways to raise temperature of system. One way is give heat. If you do some work using some spoon, if you do mechanical work, then that can also, due to the frictional force, it can dissipate energy and increase the temperature of the water molecule. End result is the same. That kinetic energy is the internal energy. So internal energy of ideal gas, for example, is kinetic energy of the gas molecule. And kinetic energy, we learned that is nothing but temperature. So if temperature change is zero for ideal gas, then internal energy does not change. Basically, so zeroth law is related to the existence of temperature. The first law of thermodynamics is related to existence of how internal energy can be raised due to the energy conservation. Internal energy means it's nothing but kinetic energy of the whole system. How can we increase the total kinetic energy of a system? We can either add heat to the system or work can be done on the system. Due to the energy conservation, Q plus W, added heat plus work done on the system, should be equal to the change in the kinetic energy of the system, internal energy of the system, delta U. So delta U is equal to Q plus W. This is the first law of thermodynamics, which is very, very important throughout this semester. And we here, for example, if we consider isolated system, no matter or no energy transfer, and work done is zero, then kinetic energy increase is zero. So how do we express thermodynamic state of ideal gas? Ideal gas in thermodynamic equilibrium. What is thermodynamic equilibrium? Thermodynamic equilibrium means that and other parameters such as pressure, volume, temperature is well defined. That's what we called. That state is what we call thermodynamic equilibrium. So, for example, if the system is not in thermodynamic equilibrium, this parameter, pressure, volume, temperature, is not defined. We don't know. We cannot tell what is temperature of the system, what is the pressure or volume. Once the system, ideal gas, is in thermodynamic equilibrium, these parameters are well defined, and these parameters follow what we learned, the ideal gas law. Because due to this ideal gas law, we know we don't have to know all three parameters, pressure, volume, and temperature, all three temperature, because once pressure and volume are known, temperature is automatically determined. So for to express thermodynamic state of ideal gas, it's enough to express P and PV diagram. Okay, any state in thermodynamic equilibrium can be expressed as a point on a PV diagram, or you can use TV or TV, whatever two parameters diagram. Here you can use any two parameters, but throughout this chapter we will. But remember, still you should be able to understand if the diagram is drawn instead of PV, PT or PV, TV or whatever. You can easily, using the ideal gas law, you should be able to derive the leftover parameter. There are two categorized as two processes: reversible process, irreversible process. What is the difference between these two? Reversible process is slow process. Irreversible process is fast process. Slow process means during this, for example, this is initial state and this is final thermodynamic state. So pressure, volume increase during this process, and also pressure increase, and also temperature increase, because PV equals nRT. If pressure, volume increase, temperature also increase. So all three parameters increase during this process. For reversible process, during this process, we know path it follows, the system follows, because during these processes, all three parameters are well defined. and the system remains always in thermodynamic equilibrium. I told you, right? If the system is not in thermodynamic equilibrium, these parameters are not defined. But during this reversible process, the system remains always in thermodynamic equilibrium, and during all these processes, we know what these three parameters are. So we know the path. Follow the path in PV diagram. And you can reversibly, from final state, you can reversibly go back to by following this path, go back to the initial state slowly. That's reversible process. On the other hand, in reversible process, system goes temporarily out of equilibrium. So that means we don't know the path because the parameter PVT are not well defined during this process. We only know initial and final state. Although the system has no well-defined path in PV diagram, it ends up, and later it'll end up in equilibrium, right? After sudden, fast process, even if we don't know which path it follow, but we know, the final state after it becomes equilibrium. So we know the end state and the first initial state, but we don't know which path it followed. That's a reversible process. Because during the process, it's so fast, temporarily out of equilibrium, so the parameters PVT are not defined. We will learn 4 basic ideal gas processes. We will apply first law of thermodynamics in each processes to find what is work done on the system and what is internal energy change and so on. First, isothermal process. Isothermal process means during the process, temperature is maintained constant. Constant volume process is literally volume doesn't change throughout the process. So V is constant. Only pressure changes. So then work should be done. Okay, now isobaric processes, meaning during the processes, pressure is constant. Then work done on the gas would be area underneath this PV diagram. So adiabatic process, meaning no heat transfer across the system. This is the end of this lecture. Let's end the chapter 18. Thank you.